Yusufeli Hydroelectric Power Project, under construction in the Artvin province of Turkey, involves an arch dam along with a 558 megawatt hydropower plant of the Koruk River. The project is owned by the General Directorate of State Hydraulic Works Turkey, while a consortium of Lema Constructions, Cengiz Construction and a Colin Construction Company has been engaged in building the facility. The construction works of the project were started with a groundbreaking ceremony held in February 2013, with the start of the commercial operation expected by June 2021. At full capacity, the Yusufeli Hydroelectric Power Station is expected to generate approximately 1,888,000,000 kilowatt-hours of electricity annually. The Yusufeli Dam and Hydroelectric Power Project is located on the Koruk River, approximately 10 kilometers downstream of Yusufeli, in the Artvin province, in the eastern Black Sea region of Turkey. The project site lies upstream of the Borcha Muratli and the Derinir hydroelectric power plants. Yusufeli Hydroelectric Power Project makeup. The Yusufeli Hydroelectric Power Project consists of 275-meter tall double curvature concrete arch dam and a power plant equipped with three 186 megawatt vertical axis Francis turbine units. Each turbine unit is designed to operate with a rated head of 191 meters and a rated discharge of 107 cubic meters per second. The Yusufeli Dam created a 33.63 square kilometers reservoir area with a total storage capacity of approximately 2.2 billion cubic meters. The maximum crest elevation at the crest line of the dam are 750 meters and 490 meters respectively. The dam project also involves the 4 balanced cantilever viaducts, including the 644-meter long Takale Viaduct, the 695-meter long Yusufeli Viaduct, the 340 long Yusufeli Dam Viaduct, and a 530 meters long shielding carbide, along with the construction of the 110 kilometers of road, 45 tunnels, 22 bridges, and 92 culverts. The other components of the project include the main power transformers, a 380 kilowatt switchyard, a long measuring and a protection equipment. For them and the facilities, a total of 8,353 meter survey drillings, 391,954 contact consolidation injection and drainage design are executed. The spillway located on the body is designed in a frontal take with 3 spans, each 11.50 meters long, with an 8.5 meter long radial gate, and with a discharge capacity of 2,940 cubic meters per second. The water discharged from the 3 compartment spillway with a discharge capacity of 2,940 cubic meters in a second and located on the dam body is collected in a plunge pool, which is constructed to be 130 meters long and to has 35 meter base width, with 3-meter linking thickness and a bottom and with reinforced base and the side walls. A breakwater is a permanent structure constructed at a coastal area to protect against tides, currents, waves, and storm surges. Breakwaters have been built since antiquity to protect anchorages, helping isolate vessels from the marine hazards such as wind-driven waves. A breakwater, also known in some contexts as a jetty or a mole, may be connected to land or freestanding, and may contain a walkway or road for a vehicle access. X-Block. Discover how to 16,000 X-Block, which will constitute the new seawall of the Port of Calais, are manufactured and installed. Calais Port 2015 is one of the most important fresh infrastructure projects of the decade, with the creation of more than 4.5 kilometers of dikes, one of which is more than 3 kilometers long. This project represents a remarkable technical challenge on the sea. The large cast concrete structure has a front shape. An automated production plant of X-Block was designed and built. The aggregates stored it according to the practical size and transported to the concrete plant, where they are mixed with the cement and the water. Samples of fresh concrete are then analyzed in the laboratory. These characteristics, which are controlled in order to guarantee impeccable quality and traceable when the concrete is ready. It is sent to the fabrication plant to be introduced into the molds of different sizes. 28 to 40 X blocks are cast per day depending on the template's volume. The factory can produce blocks between 4 and 14 cubic meters. After concrete is poured into the mold, it will go through a drying line, where the concrete will achieve a certain hardness. Immediately after dismantling, the mold will be cleaned and oiled for refuse after 2 days of drying. The block will be taken to temporary outdoor storage to await transportation. Transportation is also designed according to the transportation needs of the projects. Special heavy equipment is arranged to transport blocks of X. Not only is it heavy and extremely bulky, so the transportation requires specialized trucks. The chassis and the trunk were designed for transportability. Special roads were opened for faster and easier transportation. To be able to install X blocks perfectly requires a gyroscope device called GDP. This device is affixed on the mold and allows installation workers to determine the position and height of the block. From there, installers can easily align the most appropriate position of the X blocks can take their effect. Thanks to the modern equipment, the safest and the most responsible process, 16,000 X blocks were installed extremely quickly. Tetrapods. Tetrapods are shaped concrete blocks designed to protect the coastline from erosion. Pouring hydraulic concrete into special steel molds produces tetrapods. Tetrapods are sure structures that have proven their effectiveness in coastline protection in different countries. The special shape gives stability to the structure and also enables strong coupling among the items, which provides a guaranteed protection against the waves. For example, in Japan, where forces of nature show themselves often, the coastline is equipped with a four-ledge that protects from erosion. Moreover, tetrapods have been widely used to provide protection for port areas and ships. Assembled tetrapod steel mold structure represents four flattened cones joined by bases. And constructed tetrapod molds are dismountable. They consist of the one lower part, then base and three shape-forming pieces. The concrete mixture is poured through the upper neck of the construction. The molds are made of the metal sheets with reinforcement along the outline. Tetrapod production with steel molds requires adherence to simple process operations: mold coating, mounting, hydraulic concrete pouring, concrete mixture consideration by trembles, alternating curing and a product, tetrapod dismantling, mold cleaning up. Tetrapod steel molds are a complex technical construction, and their production requires high qualified specialists on every stage of production. Caisson. Caisson breakwaters typically have vertical sides and are usually erected where it is desirable to berth and one or more vessels on the inner face of the breakwater. They use the mass of the caisson and the fill with it to resist the overturning forces applied by waves hitting them. They are relatively expensive to construct in shallow water, but in a deeper sites they can offer a significant saving over revetment breakwaters. An additional rubble mound is sometimes placed in front of the vertical structure in order to absorb wave energy and thus reduce wave reflection and horizontal wave pressure on the vertical wall. Such a design provides additional protection of the sea side and a quay wall on the inner side of the breakwater, but it can enhance wave overtopping. Thanks to its versatility, resistance, and durability, the caisson technology has become the most innovative method for tackling a harbor construction project. This terminal, which required 21,000 tons of steel and 350,000 cubic meters of concrete, was built with Hydroelectric technology. In total, 2,800 meters of protection dikes have been built using Hydroelectric concrete cushion technology. A total of 42 floating drawers have been used. The use of the technology to build the breakwater has allowed a reduction of 8.5 million tons of stones in the rockfall. In addition, it has avoided the emission of 100 tons of CO2. Seawall, Westerland, is a seaside resort and a former municipality located on the German North Sea island of Sylt. During storm surges, Sylt is particularly affected by sand being torn away. For this reason, Westerland has been protected by a sea wall for decades. However, increasing erosion and a rising sea level make it necessary to strengthen and raise the height of the structure. Renovate a section with a total length of 140 meters. The aim was to increase the wall height by 0.80 meters and thereby bring it to the plus 6.95 meters standard height, with a possibility of increasing the wall by a further 0.50 meters. 180 pieces of micropiles, each 15.80 meters long, 57 pieces of prefabricated reinforced concrete wall parts, 13 tons each, 240 meters wide, 4.40 meters high, 57 pieces of prefabricated reinforced concrete wall head elements, 3 tons each, 2.40 meters wide, 1.5 meter high, 4,000 cubic meters of soil excavation.